welcome to the review session for the ESSC 102 Unit 1 mini test. It's our first exam for the class. It's not worth as many points as a unit exam, but I do that intentionally to kind of try to give you like a little sort of small sort of morsel of what a bigger exam is going to be like, so you can kind of ease into the class instead of just jumping into the deep end. So I'm going to be doing share screen a lot. I'm going to be attempting something with like a drawing tablet at some point. If it's really, really ugly, I'm sorry. I'm a terrible artist. But there's one question that we're going to go over that really, really helps to be able to draw it out by hand. And for you to be able to draw it, it tends to just make more sense than, trying to explain it purely through text. So we'll see how that goes in a little bit. I'm going to go ahead and do some share screen business so I can take you guys to Moodle. We could get into the review questions and go from there. So here we go. You guys should now be seeing my screen. Hopefully you can hear me, see my screen. If at any point you have questions, you're welcome to type them, but it might take me a minute to get back there. Your other option is just turning the mic on and just shouting out at me. I don't mind if you interrupt me at any given time. I'm primarily going to go through the review questions because it's a really good way of targeting concepts, but I'm going to start by showing you some other things that you can use to prep for the test. The test does start tomorrow. I'll show you where to find that and everything else. So we'll get out of this infinite echo chamber of screens here and go over to the wrong class. Right. Okay. Sorry. I was doing a review for 101 before this. So here we go. This is the right class. I'm going to set it up the same way you guys see it as a student. Hide this down here. Yeah, that's our space background. That's what we want. We'll go into Unit 1, and what you've hopefully gotten through so far are the first 5 lectures, and that's the weather part of weather and climate. I divided up intentionally that way. The rest of the units have more like a 4 and 4, like 4 for the mini test, and then the final 4 are plus the first 4 are the 8 for the unit exam. This one I divided up a little differently so I could just have all of weather, so that's short-term climate, all in one lecture. And I'm sure you've gone through and checked all this out already, but for each lecture, you've got, of course, the lecture itself, the outline. And if you're looking for what most people consider like a study guide for the exam, you can't really do better than the outline. That's more of like, here's a list of all the stuff you need to know for the exam. That's what most people are, thinking of when they think of study guide. The review questions don't work that way. They're not comprehensive. It's essentially like, a way of approaching the material that kind of targets more of the big picture concepts and less of that rote memorization of definitions. And that's what people tend to have the hardest time with. So someone who goes to like Quizlet, tries to just sort of memorize a set of notes, takes the exam, doesn't do as well as they wanted to, might have gotten through some of the more jargony kind of definition questions, but then they don't really understand these big processes. And even in a multiple choice test, you have to be able to understand those processes. So anyway, long story short, the lecture outline, that makes a better sort of like study guide list of material. The review questions that we're going to be doing today, they're going to get you to that next step of understanding. Then the quizzes that have been closing on Tuesdays for the first couple of weeks. So we have the first 5 lectures. We're going to be doing the review questions from those 5 lectures. And then there's just a wall of stuff for the mini test here. So the mini test is worth 10% of your overall grade, or 50 points out of 500. So it's worth half of the total amount of points that a unit exam would be worth. That will be worth in total. It's only based on the first 5 lectures. It does require the Respondus lockdown browser. A lot of you had my ESSC 101 class, so you know all about it. You probably already have the Respondus class, lockdown browser already set up. If you don't, it's no problem. You are basically prompted to download it before you even start the test, so you can't not use it. You can also just get all the tech out of the way beforehand by using this Respondus lockdown browser check. And it's just basically, kind of sets everything up. And as long as it works there, it should work down here too. But anything that can happen will happen, right? That's like one variation, I think, of Murphy's Law, so especially when you talk about like negative things and tech not working the way it's supposed to. So I always say take the exam as early during the window as possible. The exam will open tomorrow at 6 p.m. We'll close the following day at 6 p.m. So tomorrow, Monday, 6 p.m. through Tuesday, 6 p.m., that 24-hour period, that's when you have to take the mini test. The Respondus lockdown browser check is essentially there to make sure everybody's taking it the way that it's supposed to be taken. 95% of the time, I don't watch those videos, so don't feel like weird that I'm watching you the whole time you're taking the test. I only ever really watch the videos if the browser software prompts me to do so because it's flagged for some reason. Sometimes that's somebody walked behind you and it's not a big deal and I'm not really worried about it. Sometimes it's, like somebody last semester put a Post-it in front of the webcam, and I watched them do it in the video. So that was a 0. And it's basically just there to make sure you're not using your notes, a textbook, a phone, all of these things that you're obviously not supposed to use while taking a test that's based on your understanding of the material. So that's the whole spiel there. The test is multiple choice and true false, 10 multiple choice questions and 5 true false. I heard a bling a minute ago that might be somebody writing over here in the messages. So let me check this. The exam is not open notes. Yeah, it's it's basically just closed everything, and that's what the whole Respondus browser is effectively there to do, is to sort of support that. I'm glad it's making a beep whenever somebody types. It used to not do that, so I'd go back and 12 people would have questions, and I didn't really know because I was on this other screen. So that's a good thing. All right, the other thing here, the review questions. Eventually, the same document down at the bottom will be where one of the extra credit assignment questions comes from. This is the same document. It's just all of them as opposed to only the first 6 questions. So this down here, it's already opened, but it's not due until the next exam, which is the week before Mardi Gras. One of those questions will come from the review document. And you basically type up your answer as long as it's correct, factually accurate, and at least 100 words, then you'll get the points for it. So without any further stalling, let's get into this Word document and let's start rolling through this. I'm going to make the font way bigger. So hopefully within a window on a small device, you should still be able to see this. If not, please let me know. So I'm zooming and doubling the size on this. Enable editing, and hopefully you'll be able to see this. So, okay, before we get into content and actually reviewing material, does anybody have any logistical questions about taking the exam? All right, if any questions occur to you later on, just dive in and ask. Okay, so one of these questions a little bit further down, particularly question 3, is when I'm going to get this device involved. I have a drawing tablet that I'm not very good at using, but we're going to give it a shot. So these all are seemingly simple questions, but once you start digging into it, you realize I spent maybe most of lecture 1 talking about how do temperature and humidity control air pressure. So they get a bit dense. So these are all in chronological order. So the first 2 questions come from lecture 1. The 3rd question comes from lecture 2. The 4th question comes from lecture 4. And then so does 5. Question 6, I cover at the beginning of the hurricane lecture, which is lecture 5. So starting up here at the top, starting with how do temperature and humidity control air pressure, this is a really important distinction because these two factors, temperature and humidity, are essentially just what air pressure is. The only two things in the Earth's atmosphere that can really control variations in air pressure are variations in temperature and humidity. The only other thing I can think of is altitude, distance away from the Earth's surface. But when you start to think about things that are controlling weather, we already correct for changes in elevation. So it really just boils down to these two things, temperature and humidity. Temperature controls air pressure by effectively controlling the particle density of gas in the atmosphere. So what that means is the gas that makes up the atmosphere in some given space, like you walk outside and you're breathing in that gas, you're breathing in the oxygen and the nitrogen, argon, a little bit of carbon dioxide. It's going to be more closely packed, more closely spaced whenever the temperature is cold. So on a cold day like today, you know that the air pressure itself is denser, right? The particles are more closely spaced together. There's more particles in total in my front yard in the atmosphere than there would be on a hot day. So by controlling the particle density of gas in the atmosphere, I'm not going to write in complete sentences, so you can kind of stretch this as you will. By controlling the particle density of gas in the atmosphere, this means that high density, let's see, let's word it like this. Cold equals high density equals high pressure. And comparatively warm air means low density means low pressure. So comparatively, temperature has an even bigger effect on air pressure than humidity does. But humidity is an important factor too. The most important gas that is variable in the atmosphere that might change in concentration from one location to the next is humidity. I feel like it's getting dark in here because it's getting dark outside. I guess it doesn't matter. So humidity is going to be the factor that's, of course, tied to the amount of water vapor in the atmosphere. The amount of water vapor is going to be the biggest thing that can fluctuate. So humidity is just changes in the total amount of water vapor in the atmosphere. And water vapor weighs less than most of the dry components of the atmosphere. So what this means is more humidity. Well, let's start with less humidity. Less humidity means less humidity, meaning it's drier, means the atmosphere actually weighs more, means higher pressure. More humidity means the atmosphere actually weighs less, means lower pressure. Now, in order for that to make sense, because if you're thinking about it as adding something and not taking away anything else, then this doesn't really make a whole lot of sense. But you have to also go back to this idea that if there's more water vapor in the atmosphere, it means there's less of the dry components. And the dry components are the things that actually weigh more. So it's almost like that humidity is displacing the dry components. So you're taking out something that's heavy and replacing it with something light. So therefore, you would then have this effect on air pressure that would make it more light. So the other thing to come back to here, the thing that I hope is going to sort of make this all come together and make a little bit more sense, is actually over here in Moodle at the very top of this unit tab. So over here, you have high pressure versus low pressure. The high pressure air has a much higher particle density. All of these invisible components of the atmosphere are actually more closely spaced. Over here with the low pressure system, that's going to be less closely spaced. And then what's not pictured here is really the effect on humidity. But assume over here that not only are these particles more distantly spaced, but some of those particles, being water vapor, are actually lighter. So both have an effect on pressure. Air always, always, always moves from high pressure to low pressure. So if it's cold and dry, the air is high pressure. It moves away from that point source on Earth, like water running downhill. If the air is hot and humid, then air moves towards that point. It's like a low spot on planet Earth, almost like water running towards that spot. But this is in terms of pressure in the atmosphere, not elevation. So hopefully that makes sense. Just come back to density versus weight. Temperature affects density, humidity affects the weight. So they both have different ways of affecting air pressure, but both end up affecting that air pressure and changing it in those different ways. So let me go back over here, make sure it's all making sense. Anybody have any questions from that first review question so far? Or is it basically sort of ringing true? Cool. Okay. All right. So I'm going with the logic that no noise means everybody's good. So by all means, if you're confused, shout at me. Get vocal. I know I'm presenting to everyone. Okay. Yeah. I like it when my computer tells me things I already know. Blah. Anyway. I'm being sarcastic. I don't like it when computers tell me things I already know. Okay. Oh, I'm paranoid all of a sudden that I forgot to record this. This is definitely being recorded, right? Record in progress. Cool. Okay. Yes, I know. All right. Sorry, guys. I got a little silly there for a sec. But second question. This is material from the very end of lecture 1. So most of lecture 1 was just air pressure and what controls it, all that good stuff. The second question is towards the end of lecture 1. It's about how the atmosphere is subdivided into layers. I'm going to turn one light on because it's getting really kind of dark in here. Let's see if that helps at all. Probably not. Oh, well, I can see a little better. That's a good start. Describe how the atmosphere is subdivided into layers. Describe each layer. Now, the first part of this question is actually the most important. The atmosphere being subdivided into layers is important because that we know why it's subdivided into those layers, why we distinguish each of these 4 layers. And then we go about describing the layers and naming them. Nadia. Warm air rises and cool air sinks. Hot, humid air rises over cold, dry air. Correct. So the reason for this is because you've got not just what's going on the Earth's surface, but also what's going on with elevation. And so it's kind of like hot air rising in your house, making your attic hot, or oil and water separating. That might be a better analogy. The oil rises up above the water because it's less dense. So then the hot air does the same thing when compared to the cold air. And then that's the basic premise of why most weather happens. It's just the hot, humid air trying to get where it wants to go, which is up, further up in the atmosphere. And along the way, you form clouds and storms. So does that hopefully answer your question? Let me know if you have any follow-up questions or if I got derailed and all at that point. Okay, cool, thank you. I like the smiley face, thank you. All right, so going back over here, describe how the atmosphere is subdivided into layers. First off, the atmosphere is subdivided into layers based on whether temperature is increasing or decreasing away from the surface in that layer or zone. Or in other words, the structure of the atmosphere is based on thermal variations. So that is more important to me, that you understand why we break it down into these layers than what the names of the layers are. So from the surface upwards, you have the troposphere, where weather happens and where temperature is decreasing. It's the first 7 miles of the Earth's atmosphere. I don't expect you to know that. In fact, 99% of the time, I don't really expect you to memorize numbers. That's not a good use of your time. That's not what like a general class not intended for science majors should really be about. I'm more interested in you understanding these sort of like broader concepts. So I digress. The troposphere is first, where most weather's happening, where most cloud formation is happening. The next layer is called the stratosphere. This is also where ozone exists, the ozone layer, well, most ozone. And then temperature is increasing in that zone. The next is called the mesosphere. And if it seems like a weird word or too wordy or something, just know that meso means middle. And I swear like 90% of science breaks down into these ridiculously simple terms if you just know what some basic prefixes mean, you know, like meso meaning middle. So many things have meso in the title. So mesosphere is where most meteors break up. I think that's the kind of little fun factoid that I added in the notes, but that's not really all that important. More important is that temperature turns around and is decreasing again. And then finally, in the last layer, the thermosphere, temperature actually increases again. Now, the increase and decrease in temperature is relevant, is related to the total concentration of gas in each of these layers, so it's relative. So, you know, the fact that the thermosphere is where temperature is increasing doesn't mean that it's necessarily going to be the same sort of temperatures that we get on the Earth's surface. You know, just that, you know, from the bottom of that zone to the top of that zone, temperature continues to increase. So certainly the first part of this is the most important. And then maybe just know these zones in relation to each other. The troposphere is first, the thermosphere is last. Okay, so that's question 2, and that's the end of the questions that relate back to lecture 1. The way, and maybe I should have led with this, but the way I cover meteorology is really weird because I'm a geologist and I definitely like to try to get to as much astronomy as possible in the semester. So I definitely distill down a lot of meteorology and just put it into really like a few lectures here. You know, so as far as book chapters go, I cover the book really, really quickly, but I don't cover it in any kind of detail. I would really only go back to particularly the extreme weather and climate book if you have something very specific that you want to read up on and have it make a little bit more sense. And then you can check out the second page of the syllabus and it shows you which book chapters relate to which lectures, but it's always multiple chapters per lecture. So again, you know, particularly with weather and climate, I cover it very differently than the textbook, and I don't cover it in nearly the same amount of detail. Okay, question 3 is where I'm going to attempt to draw something, but we'll get there in just a second. This is probably the most important question that I want to actually take the time to go over. You know, like if we run out of time, oops, I'm trying to drop things over here. If we run out of time and and don't get to like maybe questions 5 and 6, I know you guys are going to basically still be okay. So 3 is the one I definitely want to spend a minute on. Now, this is the main stuff that I cover as part of lecture 2. This is, effectively why the global circulation of the atmosphere happens. It happens as a result of these sort of primary forces that control everything. So I sum this up as, what are the 3 major factors that create and deflect winds? And I kind of word it this way in the notes. I go, here's the first factor, second, and third. And within each of those, I add this, this sort of view of what this actually looks like on the real world. It's covered very differently in the book as 2 separate chapters that I kind of meld together. I hope it makes more sense this way. So what are the 3 major factors that create and deflect winds? Explain each of these forces and describe how they influence the global circulation of the atmosphere. The first of these 3 forces is called the pressure gradient force. It can be summed up as PGF. And this just really simply states that air has to move from high to low pressure. So that's something we even already talked about in the first lecture and in that first question, that cold, dry air is high pressure, hot, humid air is low pressure, and air has to move from high to low pressure. I'll add in the extra complexity that the bigger the difference in pressure over the shorter distance means air has to move faster. So there's a speed, there's a rate that's calculated as part of this too, or it could be calculated if we were actually going to do the math. I'm not going to put you guys through that. So the pressure gradient force just means that anywhere on Earth, and that's key, anywhere on Earth, air always moves from high pressure to low pressure. What this means, as far as the global circulation of the atmosphere goes, is that air wants to move from where it's cold and dry to where it's hot and humid. And even if you haven't even watched this particular lecture, you know that where it's cold and dry has to be the polar regions, where it's hot and humid has to be the equatorial regions, the equator. So as far as this global circulation of the atmosphere, this means air wants to move, I'll word it like that intentionally, from the cold, dry, high pressure polar regions of Earth to the hot, humid, low pressure equatorial regions. And that is the first major force that creates and deflects winds. In fact, it basically is the creator of winds. There would not be wind if it wasn't for differences in pressure. So the second part of this, and maybe I should go through and number it since it's 3 forces. I want a space there. No, fine. Okay. The second force is the Coriolis Force, sometimes abbreviated as C little o f. Moving air, or anything else moving on Earth, Santa in a sleigh, water, anything moving across big distances on the Earth, you in an airplane, anything moving, including air. So I'm just going to sum it up as air since we're talking about the atmosphere. Moving air is deflected because of the Earth's rotation. And this deflection occurs to the right in the northern hemisphere, north of the equator, and to the left in the southern hemisphere. Last part, 3. This is where I sum up a whole bunch of miscellaneous details. Non-uniform Earth friction clause. So we know that first, air wants to move from high to low pressure, so air wants to move from the poles to the equator. As it's moving from the poles to the equator, it gets deflected because the Earth is rotating. And finally, this third part, the non-uniform friction thing. Moving air slows and is deflected and complicated by the non-uniformity of the Earth, which basically just means this is dependent on there being differences in pressure above air versus water, or above continents versus oceans, and friction due to land masses. So 3 basically just sort of sums up as it's complicated. You know, when you actually look at pressure belts on Earth, they're not ideal because the Earth is not ideal. The Earth is not smooth and completely uniform in texture. And all of that is going to cause the pressure belts to become more complicated. Now, this is where, as promised, I'm just starting to try to draw something. It could fail completely. I could get massively tangled up in wires, but bear with me. We're going to try to make something happen here. I'm also going to try to move 12 things on my desk so I can move the keyboard over and do that. So let me go back to the here for just a second, see if does anybody have any questions. No, I think everything's good so far. So I'm going to come over here to paint. Now, one of the hardest things for me to teach when I set about recording all of these lectures as telecourses, it was this particular subject, because I love to actually draw it out by hand. And I promise, if you actually take a piece of paper and draw this out by hand, then this whole idea of why you get the prevailing winds, why they seem opposite in these different parts of the Northern Hemisphere, it definitely makes a lot of sense. But of course, this makes it a little bit more complicated since I'm trying to do all of this through a webcam. So bear with me here. I'm going to, is this thing even on? Let's see. Ooh, look, it is on. Okay, perfect. First, I'm going to draw a very, hopefully not completely terrible version of the Northern Hemisphere. So I'm basically going to attempt to draw like a half circle here. Okay, not as pretty as if I was doing it on a chalkboard, but it'll work. Okay. So this is everything north of the equator, and the equator is 0 degrees. This is 30 degrees. And this is 60 degrees. And of course, this is the latitude north of the equator. This, of course, up here is 90 degrees north, i.e. the North Pole. So the first thing we need is to figure out where it's cold and dry. So up here at the polar regions, this is going to be where it's cold and dry. So where it's cold and dry, we have high pressure air. We have low pressure air where it's hot and humid, and that's down here at the equator. So I'm going to put a bunch of L's across the equator down here. It's a little crooked, unlike the real Earth, where the equator is not crooked, but you guys can bear with me here. Maybe I should even go back and label this whole thing. So again, this is the Northern Hemisphere. So in black, I'm going to show what happens as the air wants to move from where it's cold and dry and high pressure to down here where it's low and where it's hot and humid. as the air, and it helps if you're actually drawing this out on a sheet of paper. This is where I like to tell everybody to take their paper and flip it upside down. I can't do that here. That's a little too complicated. But if you take this and flip it upside down, I think it'll make a little bit more sense when I say the air is actually deflected to the right. So the air wants to move from the high pressure to the low pressure. And if the Earth were not rotating at all, then the air would smoothly move all the way down from the poles to the equator. And it would do the same thing in the southern hemisphere. But the Earth is rotating, and it's rotating in this general direction. It's rotating to the east. That's why the sun rises in the east. So what this means is as air is moving from the cold, dry poles south, it gets deflected to the right. Now, this is 100% going to look like a left arrow, but you have to think about it from the perspective of coming from here and getting deflected to the right. So this is where I'm saying this is going to make more sense if you turn your paper upside down as you're drawing this, because you'll actually be looking down the arrow as you're thinking about air, maybe like starting up here and then ultimately winding up down here. It's moving down and then turning right. So what this does is it sets up another belt of low pressure on Earth right here. And anywhere in the world, you've got this zone of low pressure at roughly 60 degrees. That non-uniformity of the Earth thing makes it a little bit more complicated. So anywhere where you have low pressure, this is pulling air up from below. So that sets up a zone of high pressure at 30 degrees. And if I go back to my black to show the arrows, that means if I start down here at 30 degrees and move up, I'm moving up, I'm moving up, I'm moving up, I'm deflected to the right again, because Coriolis for deflection is always going to be to the right. Same thing over here. If I'm moving up, I'm moving towards from high to low, and I'm deflected to the right. So you get these two different wind directions, one that's coming out of the east and moving west, and then one that's coming out of the west and moving east, because you have different points of origin. You know, just like on the video, I guess this would probably look, this is my right hand, but it would be to your left. It's the same thing with air moving up from 30 degrees versus moving down from 90 degrees. And I hope that makes sense. So finally, the last thing we have to look at down here is high pressure air at 30 degrees moving south to the equator and then getting deflected right. And the same thing's going to happen as 90 to 60 degrees. Air's going to be moving. Oops, this is where this all breaks down. Okay. I tripped on the cord. Here we go. To the right. So this is where the prevailing winds come from. And the prevailing winds are the steering currents for all big meteorological things on Earth. The polar easterlies, the westerlies, and the trade winds. I would show you what this looks like in the upper atmosphere, but I'm afraid it's probably going to surpass my ability to draw on this kind of funky drawing tablet and trip over wires and stuff. So I'm going to leave it as is. So it really, I promise, helps if you actually draw this out for yourself. You'll kind of be able to make more sense of how all of this deflection is actually just the Coriolis force deflecting things to the right and having different points of origin. And then this builds all of these prevailing winds. Now, the two big prevailing winds that are really important for us are the westerlies and the trade winds, because we exist right at 30 degrees. Now, because 30 degrees is supposed to be a high, we're supposed to live in a desert, but we don't because we also live next to an ocean. And so that's where that third complexity comes back in. So it's kind of like that whole picture I just showed you is really sort of like the pressure gradient force plus the Coriolis force. If you ignore a lot of the other complexities on Earth, you know, like if you basically just make Earth sort of like Jupiter, just like a gaseous object, then we would only really have global circulation of the atmosphere that was defined by these two forces. Okay, so I'll go back. Let's see. I'll go back here for just a second. If you wanted to, I guess this would probably be a good time to maybe just screenshot this picture if you wanted to look at it in any more detail. If you're like, oh, that's a really ugly version of this, then I've got various animations and images of essentially the same thing in lecture 2. But I kind of like the simpler version. It makes more sense in my mind. So maybe it'll do the same thing for you. Now I'm going to go back over to the group chat and see if there are any questions. How did you guys do with question 2? Did any of that make sense? Hopefully a little bit. Okay, so I'm going to go on. I'm going to actually have a sub question. I may not get to the final 2 questions, but I'm more worried about being able to describe things while I have the ability to to describe them out. And I think it tends to make more sense in the long run too. So we're going to call this 3A. I'm going totally off script here. And, oh, it doesn't like 3A. Okay, there we go. We're going to look at the difference between cyclonic and anti-cyclonic winds as a result of the pressure gradient force and the Coriolis force. So this is just another thing I want to kind of take the opportunity to draw while I can. And hopefully it'll make a little bit more sense than the lecture videos did. So cyclonic and anticyclonic winds are essentially cyclonic, meaning low pressure, and anticyclonic, are rotating weather systems on Earth that define most of our daily weather patterns. So a cyclonic system is basically any low pressure system, and that could be a hurricane, a tropical storm, an upper level low. So a few days ago when we had that cold front pass by and it was really cold and miserable, that cold front was just part of a cyclonic system. An anticyclone is not what you really typically think of as a weather system, because that's when you have nice weather. You don't really think about it as an active weather system. So we're sitting like directly under a great anticyclone right now, meaning it's high pressure, cold, dry air, and we have relatively nice weather as long as you like cold weather. So that's essentially the difference between these two things, but you're going to have their rotation be dependent upon the Coriolis force, which is why I wanted to take a minute and actually draw these things out. So what do I do? Maybe I just save this just in case. Sure, let's call it cyclonic. No, I'm sorry, let's call it question 2. Okay, and I start a new one. All right. So, oops, there I am. Okay. we're going to be drawing out a cyclone versus an anticyclone in the northern hemisphere. And I can almost hear everybody from 40 miles away through, you know, like a a setting where your cameras and your mics are turned off. I can almost still hear your brains going, am I going to have to be able to draw this on a test? No, but you still need to be able to really understand and conceptualize the difference. And so that's where things like being able to draw this out really help. You know, if you can understand it to that complexity, then there's really no multiple choice question on earth that's going to really throw you. So the cyclone over here, a cyclone in anywhere on Earth, northern or southern hemisphere, has to be a low pressure system. An anticyclone has to be a high pressure system. I'm going to use the red to show you what the pressure gradient force is doing. So red is going to be the PGF. And all this means is that air is going to want to move inwards to any low pressure system and out of any high pressure system. The next thing I'm going to draw in here is the effect of the Coriolis force. So let's start down here because this is going to make more sense. If the air is moving from below and moving into this low pressure system, but the Earth is rotating, so this cyclone is spinning, the air that's moving into it has to be deflected to the right. And that's going to be a force in this direction. So I have the arrow moving in, so my arrow is to the right over here. From here, because it's moving from, let's say from the east to make it a little less complicated than left and right, the direction that the Coriolis force is going to deflect this air is to the right, which is up. And over here. And over here. So these are just two forces, the red and the blue, the pressure gradient force and the Coriolis. The Coriolis force, I drew G for some reason, that are controlling which way these systems rotate. Finally, in a low pressure system, in a cyclone, the actual wind direction is just the sum of these two forces. So air rotates in to any center of low pressure, which could be a hurricane, an upper level low, even on a smaller scale, something like a tornado, and it rotates out of an anticyclone. So I'll go through, anticyclones are a little less important, but I'll go through, just draw my arrows on here real quickly. And you can see the air rotating out of the high pressure system. So in the northern hemisphere, cyclonic systems always have a counterclockwise rotation. Anticyclones always have a clockwise rotation. If you were in the southern hemisphere, the only difference here would be not the direction that the air wants to move, which is the red, the pressure gradient force. It would be the way that these systems rotate. So if you take effectively any hurricane out of the northern hemisphere and stick it in the southern hemisphere, it would just start rotating the other way. In the southern hemisphere, it would be a clockwise cyclonic system. You take any sort of high pressure, like the weather we're having today, stick it in the southern hemisphere, and it would rotate counterclockwise. So pressure gradient force is oriented from high to low pressure anywhere on Earth. The Coriolis force is going to depend on what hemisphere you're in. And if you're in the northern hemisphere, it's deflection to the right. So I just wanted to take that opportunity. I know it takes us off script to go through that because I think it should really help make sense out of this for the test and for the later unit exam on weather and climate. I'll do the same thing again. I'll come back to here, let you take a second to screenshot it if that's a thing that you want to do, and then we'll move on from there. So I'm going to go back over here, make sure nobody has any questions for now. What I'm going to do from here on out, those are the questions I most wanted to go over. The rest of the questions, I'm going to do a much shorter version of those. I'm going to also unplug this drawing tablet because I don't need it for the rest of these questions. Hopefully I'm unplugging the right thing. Yeah, not the webcam. I was afraid I was going to unplug the webcam for a minute and leave you guys in darkness. So I'm going to go back to my Word document over here. We're going to go through the rest of these review questions, and then I'll quickly open it for anything else you guys want to go over. Questions 7, 8, and 9 are on the last half of Unit 1, so we're not going through those. They're not going to be on the exam, so we're just going to quickly go through these. This question, describe how a supercell thunderstorm forms. How does the rotation originate? What is it called? What meteorological phenomena can originate from this rotation? Basically, what weather thing can originate from this rotation? So a supercell thunderstorm is a multi-cell thunderstorm, just meaning there's different parts of the production of that storm in various places. You know, there's a part of it that's newly originating, part that's well developed, part that's dissipating. So it's a multi-cell thunderstorm with an internal rotation called a mesocyclone. So a mesocyclone is basically a cyclonic feature that's smaller than something like a hurricane, but bigger than a little dust devil or a tornado or something. You know, so meso meaning middle means it's just middle in scale between those types of features. That internal rotation develops as a result of shear winds ahead of a cold front. And tornadoes can spawn from this rotation. I have an 8-year-old who I think would really appreciate my use of the word spawn. You know, he's always talking about things spawning because he plays a lot of video games, especially Minecraft. So a supercell thunderstorm is just a special type of thunderstorm that has that rotation. When they start calling for tornado watches, it's usually because they've been able to spot this rotation within the storm itself, not necessarily having connected down to the ground. So a tornado watch just means the weather's right for a tornado. It doesn't mean that a tornado has been spotted. A tornado warning means that they've either seen the rotation hit the ground or in something like radar, or there have actually been reports of a tornado. So this is all part of that lecture on thunderstorms and tornadoes. It's part of the lecture 4. Question 5 here. Describe the difference between the Fujita and the Saphir Simpson scale. That was really hard to spit out for some reason. The Fujita scale, or what we actually use is the enhanced Fujita scale, is the most common way to measure the intensity of tornadoes. So it's the tornado scale, and it's based on damage caused by the tornado and not any sort of measurable effect of the tornado, because more often, 99% of the time, there's no way to actually measure that before the feature actually dissipates. So it's measured on an E0 to EF, EF0 to EF5 scale, and you can make some estimate of the wind speed that caused that damage, but the actual scale itself is based on the damage. So it's an intensity scale. The Saphir-Simpson scale is the scale used in the North Atlantic to measure tropical cyclone activity, such as tropical storms and hurricanes. And we do so based on sustained wind speed. So not wind gusts, not any of the other measurable effects or after effects of the storm, like storm surge that creates a lot of damage, not the number of tornadoes it spawns, but just based solely on wind speed. So the problem here is that both of these scales have something that the other one lacks. The Fujita scale is based on this damage caused in the aftermath, but it doesn't make any sort of predictive value of what type of damage a tornado is capable of making, because there's no way to measure those variables. The Saphir-Simpson scale is limited because the winds aren't always the most devastating impact of a storm. And I don't really need to explain it any further than that to a whole crew of people that just went through Ida last fall, myself included. So it's not always the wind speed that's going to get you, although we had a whole hell of a lot of trees down. It can be the storm surge, and that was the biggest variable in Katrina. It can be tornadoes. It can be flooding, both from the storm surge or from the rainfall, or both. So there's, whenever you make a scale that's dependent on only one variable, that's always going to leave some aspect of estimating the storm up for grabs. Okay, so that's 5. I got off on a little bit of a tangent, but that's okay. And then 6. And I should probably get you guys out of here not too much later than 6. I had planned on about an hour review. Oh, let me check real quick, make sure nobody has questions. I think we're good. Cool. All right. Yes, I know. I yell at my computer a lot. I'm sorry. Describe the difference between mid-latitude cyclones, or upper-level lows, versus tropical cyclones. Include driving force, types of pressures, locations where they form, etc. Okay, so a mid-latitude cyclone was the main subject of lecture 3. We talked about air masses, fronts, and cyclonic systems, and specifically mid-latitude cyclones. A mid-latitude cyclone, i.e. upper-level low, is a low-pressure system, at least I'm going to frame this from the perspective of the Northern Hemisphere, that forms in the middle latitudes. So that's 30 to 60 degrees north. It forms because of temperature variations across the continent. Basically cold air to the north, warm air to the south, and the conflict between those, that actually generates the storm. The lowest pressure and greatest wind speeds are at the highest point in the storm, or the highest altitude. And that's why they're called upper level lows. And let's see, they are strengthened by drawing in warm air from the south and destroyed when cut off from the warm air supply. So we talked about that in the context of the notes as that point where the storm becomes occluded. That's when you're no longer drawing warm air up from the south, and warm air being low pressure, right? Hot, humid air being low pressure drops down the pressure and strengthens the storm. But when it's cut off from that, the pressure equilibrates and the storm goes away. The other type of storm we're comparing this to is anything in the tropical variety, tropical cyclones, which could be something like a hurricane or a tropical storm and so on. These are just low pressure systems that form at lower latitudes, typically 5 to 20 degrees. So far enough away from the equator that you have a substantial Coriolis force, close enough to the equator where you have warm water, but that's variable too. And once they form, they can move up further north. So they can move up even to where we are at 30 degrees and definitely further north than that. These form over the oceans as opposed to mid-latitude cyclones that form over the continents, strengthened by the hot, humid air over warm water and latent heat released through condensation. And I think that's a really important point because the process of forming the storm strengthens the storm. The process of forming these thunderstorm clouds and having condensation take place to form those clouds releases heat back into the system and strengthens the storm. And they are then weakened by contact with land masses and cold water, because it cuts it off again from that hot, humid air, which then strengthens the storm. Oh, I will add one more thing here, because we need to include the driving force strengthens the storm, the types of pressures. The lowest pressures and greatest wind speeds are at the base of these storms. And so that's basically what's making this like a lower level low as opposed to an upper level low, and makes them more dangerous as far as creating a bunch of destruction. So you have a lot bigger wind speeds to deal with something that's tropical in origin, because the lowest pressure and the greatest wind speeds are at the base of the storm right next to the surface. As opposed to upper level lows, those actually end up being more problematic for air travel because you have almost an upside down tropical cyclone where you've got your low pressure and your great wind speeds up at the top of the storm. All right, so this question in particular is basically just straight out of the very beginning of lecture 5 too. So you can go back and you can actually look at images that makes this hopefully a little bit easier to retain. So I think that's everything that I wanted to go over. I know I did a speed run through those final 3, but I find, if I make these stretch too far past an hour, I tend to super lose everybody's focus. So I will probably go ahead and we're done with the review questions. Did anybody have any topics that they wanted to go over before we clear off from here? If you come up with any in the course of studying for this exam that's going to open at 6 p.m. tomorrow night, please let me know. I'll keep checking back with the group chat, see if anybody posts any questions there. You're very welcome to do so, or email them to me, or set up another little meet like this, and I can talk through any of this material with you one-on-one. I hope you guys rock this exam. I have pretty high hopes. I think based on the kind of chatter I've been hearing, from the group chat, I feel like, I feel like you guys are digging into this. You guys are so welcome. Have a great evening. Enjoy Sunday night dinners. Thanks for bearing with me on a Sunday evening through this. And thanks for coming. You too. Thank you. Hey, sure. Would you like me to send them to you, Brandy? Let's see. Yeah, okay. I'll just email them to you. Well, I'll do that once we're off of here. Do me a favor. I don't know if I have your email saved. Send me an email and I'll reply with those text documents. You're so welcome. Alexis, did you have any questions? All right, guys. Well, I'm going to go ahead and end the meeting so I can post that for anybody who couldn't make it live. Bye, guys. You're welcome. Oh, I forgot to